Can you hear the ego in that? All right, let's go ahead and look, because we did last time, we did investigate and learn how to graph absolute value functions like this one, for example, and how to solve them if they were equal to a number, correct? So we've done this one before. And if this is equal to 4, then our setup is y1 equals y2, right? So that means that y1 of x was this function, and y2 of x was just that function. So if we just graph a constant, it's simply the line y equals 4, right? And if I do an absolute value function, say x minus 2, then it would be this, right? And we could solve for those 2 points, right?
Right.
In this system of equations. And in order to do that, what we did is we took the negative component and set it equal to 4, and we took the original one and we set it equal to 4. And we would have x equals 6, and in this case we would have x is equal to negative 2, and these would be valid solutions.
Right.
So now what happens though, and this is going to be the lecture of the day. It's not going to be this because we went over that. What happens when it's equal to a function? So I think it's interesting. So that's going to be what we're going to be doing today. Let's go ahead, and I'm going to snip this because we know that how Canva likes to be, and it'll tap us out if we don't. Now, what I like to do when I learn something new, get out your trusty dusty TI-84. Because your trusty dusty TI-84 is going to be the thing that allows you to learn the material so that you can do it by hand later on. And see, that's the beauty of technology. You might not be able to use it on a test, but why aren't you using it to learn, man? That's what it's for. Have you ever wondered why we still have them? All right. So let's go ahead and let's take a look. I know, right? So what we're going to do is I'm going to put one random function on the board. I'm going to put absolute value. We'll keep this simple. We know the plot of this looks like so. And we know that like something like maybe we're going to say this one looks like so. What if I translate one and do this? That might make a little more sense. So let's actually instead say we've got x minus 4. Let's move that over a little bit, right? And then what we have, if I expand this graph to include x squared, is we have this situation where you have a parabola intersecting the absolute value line on more than one occasion. What I mean by that, let's bring down my little graph here. What we have to do is we have to learn how to solve it when we've got another function involved. See what I'm saying? And so we're going to go over that analysis today. But notice how when we know how to graph these for example, these easier functions, notice that when we do these, it's clearly evident that, or for the most part, since x squared increases a little more rapidly than the linear behavior of absolute values, that you're not going to intersect this left side more than likely, right? So that's what that's one of the keystones, right? Is to inspect the graph first for the simpler based functions. And we're going to derive just how we deal with all of it. But if it's an absolute value function, then that means you'd have to have negative x is equal to x squared, right? But if it's negative x minus 4, so let me do that. And we're going to see, just like in our earlier video, why earlier we couldn't find x-intercepts for a translated absolute value function shifted upward. We couldn't find anything because it didn't cross the x-axis. So we should suspect here the same keystone. No crossing behavior if the domain doesn't exist, right, for that. Because the domain for this is right here for x is less than, I should put it over here. Look. Do you understand what my brain is doing? The keystone here is analyzing where this function is valid. What intervals of validity do we have? So the keystone involves the domain, and you should be asking yourself, what intervals of validity do we cast aside or use? So that is the keystone for this, and understanding how to solve these. And by knowing that, you've eliminated the point of confusion, because we know how to solve problems. We know how to solve systems somewhat. I'm going to go more into systems later after these lectures, but this is how systems behave. I have actually kind of showed you a little bit on how we solve systems. In this case, it's just one equal to the other. That's one way you solve systems. So even though this is, and again, we don't have this function, sorry about that. We've got the x minus 4 negative portion. Since we know how to graph absolute value functions and their translations, then we can simply just extend the idea of systems and our previous idea regarding the keystone of the intervals of validity on what can and can't exist. Because we know for this side that x has to exist for the left side, right, for less than 4. I actually have the wrong translation on the graph. You might have noticed that.
Yeah, I did.
Good. So that actually needs to be over here.
I figured it was wrong because it doesn't make sense.
Right. So we would have figured it out by the very idea of the logic, though. So that's the beauty of doing both. When you know how to graph and do abstract or learn one from the other, you're really increasing the amount of skill you have in your capability to solve a problem, right? And you might even catch it like I just did. Like, that's the thing. That's what I love about making mistakes. I actually love making mistakes in math because I can see, like, where I went. It's just kind of fun to me. I don't know why. Don't ask me why. So it actually might cross through both of them. I'm seeing. It does. It certainly does. I can see this. But one of the parts of the absolute value function is not. This graph looks awful. I did this one by hand, right? So let's look at this. Like, I'm not a painter today. So we've got an intersection here and here, but not with this line. So let's take a look. So we want to look at why that is. So this is going to be for x greater than or equal to 4. So we're going to look at positive x minus 4 is equal to x squared, since we know how to deal with these. And let's go ahead and tackle this. And we'll solve them by setting it equal to 0, because that's how we solve higher powers of x. So I should just keep that kind of broad. So we're going to have, on this side, x squared minus x plus 4. And since I already know that it intersects the other one, I should expect 2 solutions. So on the left side, for x less than 4, let's look. Let's try to, should we factor or synthetic? I wonder what we should do. 4 and 1, no 2 and 2, no n. It looks like this one might not have pretty solutions, because I'm not seeing a factor here. Let's test the delta first. The discriminant, b squared minus 4ac. So 1 squared minus 4 times 1 times negative 4. Definitely is a number. So that's going to be...
This one we have to use a quadratic. We have to use a discriminant, the denominator.
The reason why is because it's not pretty. Look at that. That's the square root of like a prime number.
Bro, oh my God.
Right. So synthetic division isn't flawless. Like, and that's the thing about math. Like, but don't let me fool you. Synthetic, a lot of the things that you learn to solve problems that have, I want to say, more convenient numbers, is that you can still use convenient numbers to model a system and approximate. It's not the all be all end all of what you got going on. Like, you're still good. It's just, if you want to pass your test. Or if maybe you want to save the lives of astronauts, then it does. Like, definitely need to make sure your numbers are spot on. But I'm just saying, for the layman scientist or mathematician, no big whoop. So let's go ahead and use a quadratic. There's multiple methods. That's the brand. That's why math is language of the universe. So don't get hung up on, oh, it doesn't work this time. That's just the way that it is. There's another way we can solve that problem. That's all that means. That's not a big deal. So in fact, this is how we do it for this one, which is what I'm getting at. So -1 over 2 times 1, that's that, plus or minus, and we already did that, root 17 over 2. So now we've got -1 minus root 17 over 2 for one of your solutions, and the other one is x equals -1 plus root 17 over 2. And if you put those in your calculator, right, you'll get the numerical approximation, and that's how you would finish it off. You would use your calculation to finish the rest of that problem. So I'm going to actually solve it in Mathematica real quickly. Another way we can finish it off, of course, just to show you that we are not limited as mathematicians. So let's solve. Look at that. X squared, is it minus or plus x? Let's see. Whoops. This is going to be, I shouldn't just do that. Foo. This is going to be plus x minus 4. Okay. And we will get these quadratic expressions that I'm about to show you. And to validate that they're correct, you'll see them. Mathematica likes to oversimplify. Let's go ahead and show this. So you see this, how Mathematica does it. It puts it in double brackets, makes it look complicated. Pretend they're not there, because that's just programming language. That's just the C++ that Mathematica uses. So I just want to let you know, for this side, those solutions are definitely valid there. And that's the solving feature they have in Mathematica. So good deal. But and even still, I can do an insolve, right? And I'll get the actual numerical approximations, which that's nice, right? So I got these for insolve. And this is really what you want to do when you're, or you could take the numbers, right, and put in over the numbers, but you can just get there quicker if it's simple math like this. And so you've got -2.56 and 1.56. And so those are the intercepts. But what is the coordinate? So we do have x for this portion. And if we want to know the coordinates right here, of course, then we do have on the left side, I'm running out of space. I'll just put the x for now, but just know there's a y involved here, of course. So you've got the x is equal to -2.56 approximately, and approximately x is equal to 1.56 on this side. So now we're kind of seeing how absolute value functions really affect the environment here of what's valid. But what happens for the other one? But I have an x here because graphically I know how to graph them. So apparently these are never going to touch. They approach parallel, right? So they, not quite. They actually deviate from it, but this actually gets further and further away from parallel, I should say. Actually becomes more perpendicular, really. But the reality is that they never cross. And that's what we get here. What a tragedy that these star-crossed lovers are never going to cross paths. So here we go. X squared minus x plus 4. Let's test the discriminant and see what we get. That's always the first step we need to take when we're doing things, if it's quadratic, because you can sit here and try to factor in synthetic division or waste a minute thinking about it. But let's do the b squared, so -1 squared minus 4 times 1 times 4. And what do we get? Look at this. We saved ourselves some time because we get minus 1 minus 16. But that's equal to square root of -15.
So we also get the unpleasant numbers again.
But no, it's not that. You should be seeing another keystone here. What?
It's out of the number system.
Did you say that? Is that what you said?
Yes.
Oh, then if you said that, you're right on it. That's exactly what the problem is. This is out of the real number system. Like, or you want to say this is not something you could graph or plot in the real number system. Yeah, not so conveniently. Even if it did have real roots and complex math in this situation, you cannot exactly. We cannot do anything for this one in that case, and that tells us something. That tells us that one, these never cross in the real number system. So the only solution you could ever get out of these, if any, even if it's imaginary, right? Even if it's imaginary, you probably even wouldn't get one there looking like, because they never really, you'd have to extend your circles, right? To see if there were any potential. So that's complex math. I'm not going to get into that, but I might not even be right about that. So no judgment here. But what we're going to have here is, let's finish it off. We've got x1 comma 2 is equal to negative b over 2a. Yeah. 1 over 2 plus or minus over that. And that's just going to give us this. Root 15 over 2i, proving that they never cross. There's doing that thing again. I hate it when it does that. Good grief. Anyway, that's the score here. Look, why is it doing this? It's nuts. Here we go. Now I can write. Okay. Over 2. No solution. Not real. Solutions.
So you only have like one answer.
Right. We only have one answer set. We only have two intersections between the two functions, and that was going to be the left side, negative x minus 4 equals x squared, of that absolute value function. So now you know why I do like a whole lecture on that and why I describe them as piecewise, because these can get pretty absurd, right? In fact, you might have absolute value functions that are quadratic in nature, and that's just wild. We haven't even investigated that one. So I don't even know if I'll bring that up, because that's usually not very common in high school, to be honest.
Anakin, Chancellor Palpatine is evil!